What's up? What's Gucci? What's good? What's poppin'? Vectorization is the topic for today's stream. And vectorization is a really important topic for making your machine learning algorithms computationally efficient because vectorization allows you to use the GPU or some special hardware on your computer in order to do the mathematics, the calculations of usually it's like multiplying and dealing with matrices. It allows you to do all of that in parallel, which is going to be more performant. On most computers, it'll be using a GPU. I'm not entirely sure what that looks like on the Apple Silicon processors, but I do know that Apple products tend to have their own way of dealing with that. I believe it's called Metal. It's their way of doing graphics. But don't quote me on that. So don't quote me on that, okay? So anyways, we're gonna jump into this today. Before we get started, I always, try to show up with a little bit of something extra, a little bit of a gift, a little bit of something extra you can take with you. If you check down in the description for this stream, you're gonna see that there is a list of resources. And that list of resources, I try to add some to that whenever I can. And lucky for you today, there's this new thing I got here for you. So, a good book is worth more than 1,000 words because, a good book has more than 1,000 words in it. That was a terrible joke. But anyways, a good book is really important, of your journey. A good reference book. And fortunate for you, this book that is otherwise very expensive, this book right here, Python for Data Analysis, this book retails for about $70. That's how much I paid for it. That's how much I paid for mine through the App Store. I got mine through like Apple Books or something like that. But lucky for you, there is an open access HTML version of this book that you can get by going to the link in the description of this video. And in the description of this video, the link for that it's just going to say Python for Data Analysis, and it'll come here. This is the entirety of the book that I just purchased that you can have for free. And if you are watching this video but you do not have your Python environment set up, meaning your interpreter, your environments for running various versions of the language, your packages for Numpy and pandas and all that stuff. If you need help getting just set up with using Python in general, this is where you want to go. And in this little ebook website, you go to this section here. This is section number 2. Actually, you should really start off with this preliminary section because it's going to explain some stuff to you about, some of these packages and whatever. But if you're just trying to get set up, go to this section number 2 right here and just click that. And in here, you're going to see the steps that you can follow in this section here, where you can go to install your Python interpreter. It's going to walk you through like the basics and all of that stuff. Jupyter Notebook, everything that I'm using, essentially it's going to walk you through all of those steps. So I would just recommend coming to this ebook, reading through this preliminary section here, and then see here it says it helps you install and configure Conda. For this, you're going to be using Mini Conda. You can also use Anaconda, which is the full version. Anaconda is like a package dependency environment manager. But yes, just go through here. Just go ahead and start off with section number 1. And then when you're done with that, go to section number 2. And that will basically get you going for actually working with the Python language. And then everything else from there will make sense if you're not already set up, okay? So I just wanted to let you know that that's a free resource. This is a great book. O'Reilly has incredible tutorials and workshops and all sorts of learning things. So this is a reliable source. And the nice part about doing this website as opposed to purchasing the physical book is that they do update this. And in addition to that, another nice thing about this book and this resource is that they actually, let me see if there's a link here. I know it mentions it in the book. I don't know where the link is in here. Oh, here it is. So another nice thing about this book is if you do decide to use this to supplement your Python learning, you can go to this link here in the preface section, and you can actually get access to all of the examples and like the little labs and stuff that they use in the book, you can get them on GitHub for free as well. So yes, this book is like going to be your starting point for introducing you to Python in reference to data analysis. If you don't know any programming at all, then you might need to start somewhere else. But if you're familiar with programming, like the gist of it, enough to kind of like, you know, explore different languages and whatever, and you understand like the paradigms and whatnot, then I would definitely recommend starting here, okay? So that's that. Another thing that I added to the resources down below, specific for this video, vectorization, is I added a link to my notes, the notes that you'll see here off to the right side, this right here. You can get these notes by going to my LinkedIn, and that is a link that you can find down below in the description as well. And these vectorization notes kind of just summarize some of the basic information, and also there's some examples of what vectorization looks like in comparison to a non-vectorized version of the same code. So that's all included here. And then lastly, as I always try to mention, this little video series, at least at this point right now, it's kind of based off of a Coursera class. It's a machine learning course that's there, and the link is in the description as well. So everything you need to know in order to do this and to go beyond this series is in the description. So without further ado, we're going to do some vectorization in Python. And today, this is a study session. So please don't come here for, you know, definitive answers and everything like that. I'm going to do my best to explain things as we go, but I'm learning just as much as you are. And just think about this as like pair programming. This is called OpenPair because we're working together. We're pairing together, okay? I'm here to just kind of help you, and you're here to help me. That's how we do it, okay? So everything's good, which means everything is Gucci, which means everything is Prada. And if that's what it is, then let's just go ahead and get started, okay? Okay, so that was my incredible introduction. I think I'm done rambling. Let's get serious now. Okay. Oh, that's my cat. You hear my cat in the background? Okay, so vectorization. What we're gonna do is we're just gonna play around. Before we get started, we need some dependencies here. Where am I at? Python. Okay, so I'm using Jupyter Notebook in VS Code. That's important. So if this looks a little different, don't be too alarmed. The reason why we're doing vectorization, by the way, is because now that we have moved on from doing like univariate linear regression into doing multiple linear regression, as you can see here, multiple linear regression with multiple inputs. The reason why we need to do this vectorization is because now we're going to be like multiplying sets of numbers by one another, and potentially large amounts of sets of numbers by one another. And so that could get really, really slow. And Numpy is going to be the predominant library that we use in this series right now, and also in that book, that ebook that I just showed you for data and data science and stuff for Python. Numpy is like the primary library that you'll see used for dealing with vectorization and whatnot. And I don't know exactly how everything runs under the hood, but I do know that Numpy kind of does all this stuff that allows your code to utilize your GPU acceleration and all that kind of stuff. So we're going to import that. And then just know that for some of these things, like when I import this as NP, you also see me do this for other things like pandas and matplotlib. Some of these like aliases here, these are just like standard things that you're going to see people use in general within the data science community. So these naming conventions, just try to be aware, like when something's being aliased in like this, that's probably going to be a just like a standardized thing that you're going to see a lot of people do. Okay, so there are some references here. Let's see. Okay, so Python is the programming language that we'll be using, and it has a set of numerical data types and arithmetic operations. Numpy has a library that extends the base capabilities of Python to add a richer data set, including more numerical types, vectors, matrices, and many matrix functions. Oh, sorry, maintenance is over next door, sorry. Okay, anyways, NumPy and Python work together fairly seamlessly, and Python arithmetic operators work with NumPy data types, okay? So you could use data types that are just like vanilla Python and do stuff with them without using NumPy, but they're gonna be a lot slower. And if you use NumPy, it's not gonna forbid you from doing things like just the vanilla Python way, which is what we've been doing up to this point. So don't worry too much about whether or not you're sacrificing something with NumPy. Just go ahead and use NumPy as a way to create your data structures. Okay, so, and vice versa, NumPy is interoperable with vanilla Python data types, so you can use those in NumPy as well. One of the reasons to use the NumPy data types and stuff is because if you use them, they're gonna have some additional methods and whatever that you can leverage as you work on your code. So those won't be available to you if you make your data types just strictly like vanilla Python. Okay, so the first thing we're gonna talk about is vectors. Okay, so vectors, what is a vector and how does that fit into what we're doing today? Okay, whoops, I gotta make that into Markdown. Okay, Markdown, take some notes here. Okay, so vectors are, in this specific scenario, a vector is an ordered array of numbers, okay? So what I'm understanding from this is that an ordered array of numbers means that they're indexed. They're indexed. And one way to think about the indexes, how they're like represented, is like my little example here. Whoops. In math notation, an index is usually communicated as being a subscript. Oh, I'm sorry, it's communicated as being a subscript, or it can be communicated as something that is like a superscript. It really depends on the context. It can go either way. I'm going to show you the subscript version because for multivariate linear regression, this is the way that we're going to be showing the indexes for our inputs and our weights, which there will be multiples of, a weight for every index. So when you see like this little symbol right here, like this, I'm just going to go ahead and close this. When you see this X here that has like a little arrow over it, this is like math notation that represents this this variable as being a vector. Now this is different from the vector that you might see in physics. Typically a vector in physics is like two numbers that exist in a set for magnitude and direction. In this case, a vector is just like, think of it as like an ordered list, where each index is assigned to a specific value and that order does not change unless you explicitly change it. And this arrow above the variable is like math notation for telling us that whatever we're dealing with is that. So here, x of 1, x of 2, x of 3. In this case, these are all inputs of the same category, and they're like delineated by having some index, okay? So these are all going to be treated as a set. Elements of a vector are all the same type. A vector does not, for example, contain both characters and numbers. The number of elements in an array, they're often referred to as being, as having a dimension, basically. So a vector has a dimension which is described as n. And n can be thought of, let's see, I think I might have something in my notes that might explain a little bit better. N is kind of like how we're thinking about m as being like the range or the size. N is like in multiple linear regression, n is like the number of features And the number of features in and of itself means that each of these features has a size, and the features themselves is a size for how many features that exist. So don't get n and m mixed up. N is the number of features in multiple linear regression, and m is the size of a feature in terms of its length of a specific feature. Okay. So the elements of the vector can be referenced as indexes because it's ordered. Okay. So we're going to be using Numpy, this package right here. It's arrays. Oh, excuse me. Okay. Why am I like talking like I'm teaching this? I'm really like literally studying this with you. Okay. Just chillax to yourself. Okay, so we're gonna go ahead and just like play around with some code here. Some Python examples. Okay, we're gonna just make a new code block for Python. And we're gonna call this one vector creation. With some people call it Numpy. I call it Numpy. I don't know why. Because Python Py. Okay, so we have one that we're going to create here. We're going to print these out so we can kind of see as well. Okay, so this right here, this first one, np.zeros, this should make an array with 4 zeros inside of it. That's what we're expecting. Then we're gonna do another one. Double parentheses. And we're gonna expect this one to similarly make an array with 4 zeros in it. And both of these two here, these will be the float 64 type, which I understand it to be like the default type for these NumPy arrays when we're creating numbers in them. Okay, so what we're gonna do with this one is I'm expecting this, let's see, it says returns a random float in half open interval. The results are from a continuous uniform distribution over the stated interval. I'm gonna have to come back to this. Is a lot. This is pretty complicated. So random.sample. Okay, and what I would like to do is print those out. Oops, forgot to. I'm gonna go ahead and print each of these out as well, so that we can see informaciones. Okay, so this first one, like I was expecting, I am getting my array with 4 zeros. You can see here that they are float 64, but they're zeros, so there's nothing on the right side. And then the next one here, I'm going to print out as well. Yeah, I'm going to print this out as well. Same thing, okay. And then for this third one, I really want these to be flush with one another, so I'm gonna move all these over. Okay, so for this one here, we're getting an array with 0.4, 0.7, 0.40, 0.73. I'm just gonna look up what this random.sample is doing. Yeah, I'm gonna look this up. Random underscore sample. It says returns random floats in half open interval. I don't know what half open interval means, so I'm gonna look that up now. This is how we start going down rabbit holes, I swear. This is how it all gets started. Okay, so half open interval is a set of numbers representing all the numbers between a pair of given numbers and including either of the endpoints. Okay, I get that. How does that, but how does that actually work out with this 4? This is just a 4, like, for real? Okay, so it says, so I get that part. Like, this would make more sense if it was something like, I'm just gonna see what happens if I do like 1 and, or 0 and 1. See, but like that didn't work. That's crazy. Maybe it shouldn't be in a, wait, maybe it should just be like 0 and 1. Yeah, that's a little strange to me. Okay, so the rest of it says the results are from the continuous uniform distribution over the stated interval to sample something here in like math magic language. Okay, I think if I did like this, 0, 1, no. I am definitely misunderstanding this. That's what happens. Let me see if I can find another page. Sometimes the actual documentation is not the best at explaining what something does unless you already understand it, which is a little odd. Let's see. Okay. Let's go. Okay, so this will generate numbers that are between 0. It says that, let me just go ahead and type, or separate this out. So this says that the numbers generated by random sample will be between 0.0 and 1.0. It's really like that. Now that part makes sense. That part makes sense based on what we're getting here. part that does not make sense is, what does this for mean? That's the part that doesn't make sense to me. So the first parameter is size. The size is actually optional. So if I remove this, it should still do its thing. Nope, it didn't. It says here that the size is optional. So that's a little weird. That's a little weird. Let me go back to the Numpy documentation. Okay. So the first, yeah, so it says size. It could be an int or a tuple of ints, and it's optional, but apparently it's not, because I just did it without it and it did not work. So output shape. If given the shape something something something, then okay, so values returned. What happens if this is like 5? How does it look different? Okay, let's see what this says in here. If given shape is okay, I'm just gonna take a guess here, but I'm not gonna linger on this too much. It seems like what happens when you do random is that random occurs according to some parameter that you provide, it seems like. And that sample, I think, means how many times it performs its operations, which I think will increase the true, because I've heard that nothing is truly random with programming. But if you have a higher sample, let me just look that up really quick. Sampling and random. This is why I do these like videos where I come back and like explain things concisely, because I learned so much just from like getting lost. NumPy's random number routines produce pseudo-random numbers using combinations of bit generator to create sequences and a generator to use those sequences to sample from different statistical distributions. Okay. Oh, okay. Okay, I think I understand. So random sample is one of of some amount of different types of methods that can be called against this random here. What random sample means is that there is a collection of numbers that is generated when random is called, and whenever those numbers are selected as the return of this function, then those numbers are not going to be duplicated in what you get. So for example, if you have an array, or I'll just actually put this example here in the screen so you can see it. So if you were to do like samples, this is just like from a slightly different library, but if you were to do random sample, then you can see here that the numbers are always going to be one or used once. But if you use something else like choices or whatever, it seems like you could get duplicates of the numbers. And I think in I'm gonna check out Numpy real quick just to make sure that this syncs up. But I feel like that's a good explanation. Let me just check here. Yeah, it says that Numpy random sample is comparable to the vanilla Python random.random. I'm just gonna see what happens if I do that here. Oh, I need to change this, by the way. Which one is it? I think I need to use, I think this one's fine. Why is this not working? Sure. Okay, so it says here, random variable generator X in the interval. Okay. So yeah, this is going to take the range of these two, and it's going to select some number from that, and it's only going to this doesn't say anything about a limit on like how many times a number can be returns though. This might actually be something that is like way beyond me. Figure out this exact moment. I'm not gonna lie. Random is like a pretty big topic, I've heard. It says here, random sample method. We can sample the data values and choose random data at ease. It selects random samples between 0.0 and 1.0 only. We can build a single sample as well as the entire array based on random values. Okay, so this 4 is the number of things that we're getting. Random sample. Don't really know. I'm gonna see what happens if I do like this. I think the rabbit hole for this might be a little too deep for me. I'm drowning. Okay, I'm gonna look up just one more thing. I'm gonna see what random does on its own. or backwards compatibility with previous versions of Numpy. I take it that random is not meant to be used on its own. That's what I'm understanding right now. Yeah, I'm understanding that it's just not meant to be its own thing. So within the random function or method, there are these other methods you can call. Random sample, its specific thing that the other ones don't do is that it will pick a number between this range. As far as what I was saying earlier, or was reading earlier about duplicates and whatever, I don't know about that part anymore because I don't see it in the NumPy documentation, although I've seen other people talk about this in other places I'm looking up here. So I'm not gonna integrate that into my understanding at this point. Now you can do random integers. Looks like what's rand, R-A-N-D? What is that? Oops. I think their documentation is not up to date either because it's saying that there should be a rand and that's not showing up here. I don't know, something's a little weird. But I think what's important to know here is that we can generate 4 of these floating point numbers by passing in this 4 as the argument, and then this will just generate the floating point numbers between 0 and 1. Okay, I'm not gonna stress too much about it. But you know, my curiosity is always like driving me a little crazy, so that's not new. What happens if I do that? I think I can define a shape here. I guess not. Or maybe these need to be like in parentheses. I thought I saw something like that. Yeah, so I can do a 2-dimensional, I could do 4 2-dimensional arrays of random numbers. That's pretty cool. So I guess if it's just like comma with nothing after it, it assumes it's 0. Or it assumes that this is a 1-dimensional, rather, just one-dimensional array. And then if a number is there, then it's multi-dimensional. It's like, it's a 3-dimensional array. So it's a set of arrays that each have 3 numbers. Cool. Okay. Okay, so that's nice. Let's move on to the next one here. So, a comment before I move on this is NumPy routines which create memory and fill arrays with value. This is like, I believe that NumPy is using C++ under the hood. Let me see. I think it is using, actually I don't know. I don't know if there's like some other language or whatever, but I do know that when it says memory here, this is memory that is being allocated from some type of GPU. Now, I'm not entirely sure how that works out, seeing as I'm using a M1 Mac that has its own thing going on. I don't think I need to understand how it works. in order to use it though. But my curiosity is just like killing me right now. Let me just see if I can quickly find some information on it on their website. I'm gonna bring this over so you can actually follow along. Oh wait, that's not what I wanted. Maybe this is it. So maintenance release, the most hardware, which includes. I don't know if this is going to tell me much about it. I just really want to know how, if this is using GPU hardware, how does this accommodate for the fact that the architecture of the M1 Max is different? It's integrated GPU, so I guess that's really what matters. Okay, I guess there's no difference. I mean, it's just probably something in the way that it's configured or something. I don't know. I don't know much about like the interface, I guess, for doing stuff with Mac GPUs. I know they have their thing called Metal, but I don't know. Anyways, that's too much of a tangent. I think I'm good with that for now. I think I can move on. Okay, so the next thing we're gonna do here is, let's see, we're gonna do some more. A equals p.range, and we're gonna do 4. Random.rand. I thought I just tried this rand thing and it didn't work. Now it's telling me to do it. And we're gonna print these off too so we can see the results. So a range. So it looks like, what if I do 5? If I do 5, it should count from 0 to 5 or 0 to 4. That's what I'm assuming. Yeah. Okay. So what this does is it creates a. Let me put a note up here. Creates an array with indexes, how can I say that? Length of parameter. Each item is numbered by its index. Each value is the number of its index. Okay. And then this other one here This says, looks like it's kind of doing what this random samples does. So I'm not sure what the difference is. Let's see. Yeah, that literally seems like it's the same. So this is from the continuous uniform distribution over the stated interval, whereas this one, random samples from a uniform distribution. I'm gonna look up what is random underscore sample versus rand. So it's saying here on Stack Overflow, oh, okay, so it's just saying that between this here, this rand and random sample, the difference is the input format. That's what it's telling me. And I can accept that based on what I'm seeing here. I can accept that, although I need to know like what is the difference in the format that it's actually referring to, because right now what I have here is like literally the same thing. It looks like it's the same thing. So I'm just gonna put here returns same as random sample, difference in input format. Ooh, excuse me. So if I want to do a two-dimensional array here, I know that I have to do, was it this again? Okay. With the parentheses? Okay, it doesn't matter if it's parentheses or brackets. Okay, so I know that I get that. If I do that here, does that work as well? Okay, this can only take in an integer, maybe. So this can take in an integer, tuple, or tuple of integers. So I'm just gonna put down here, can take in an integer or tuple of integers. And then this one here can only take in an integer. So I think I could still do this. Take in as separate arguments. Okay, that makes sense. So both of these do the same thing. This random.rand and random.random sample, same thing. And then so that means that this shape does not get to, I'm just gonna copy this comment here from the, it says numpy routines which allocate memory and fill arrays with value but do not accept the shape as input argument. I'm assuming it's referring to let's see. What if I do this? No. I'm sorry if y'all can hear my neighbors knocking and stuff around next door. They probably hear me too, so. I'm about to tell them to come back if they knock over here because they're supposed to give a 24-hour notice and I'm busy studying. Don't kill my vibe. And I will do it on camera. Actually, I won't do it. I'll just put it on pause, but. Okay. Okay, so moving on here. Okay, we already did this in our previous little sections here, but we can also do some NumPy arrays. NumPy array. This is what we were doing earlier when we were creating our data sets for our training data. Oops. So 5, 4, 3, 4, 3, 2, and then array 5.4, 3, 2. Don't y'all just love how raw and like just unfiltered and unedited my streams are? I have no intention of making this stuff over here pretty. Y'all could go somewhere else if y'all want that. This is really a study session for me. I don't like to edit. That's one thing about me is I don't like to edit my videos. So this whole this whole stream is really meant to just be like if we were hanging out and we were just like studying together. That's how it's meant to feel. So this is my real life. Okay, so it looks like what's happening here is if we define all of these, or if we define all of these as like integers, then it'll obviously assume that these are integers. If we do the same thing with NumPy array, and one of these is a float type, then it's going to coerce the type of the other numbers here to be floats. Now, I thought we were looking at, okay, so when it's doing this NumPy zeros here, it's going to return a data type of float, it seems. Oh, you can actually determine the data type, but it looks like it defaults to float. Okay, so that's interesting. So NumPy array, its return type, oh, you can actually coerce its data type to, says here, the desired data type for the array. If not given, then the type will be determined as the minimum type requirement to hold the objects in the sequence. Okay. Okay, that makes sense. Okay. So let me just put a comment up here. Specified as an argument. And then here, return type for array will be the minimum required to hold the data coercive. Unless specified. I wonder what would happen if, let's see, data type. I wonder, okay, so there, I'm not gonna do this right now, but I wonder what happens if you, well, I'm gonna try it. What happens if I put like a letter in there? Will it convert that? Oh wait, I put it recursively. I should probably pick something else, like do a string. Yeah, let's try that. Oh, okay, so it converted all these to strings. Interesting. Okay, so that is interesting. Okay, so that makes sense. So no matter what you put in here, you don't actually have to define a data type. It's just going to force it into whatever the minimum is. Now what happens? Okay, I said I wasn't gonna do this, so I'm doing it anyways. What happens if I put a string, but then I put in a argument that for the type, let's say float 64. Can I do that? Oh, bad. Okay, it says it cannot convert a. Now, interestingly enough, you can actually convert a string into a number. Python, let's see. Convert a string into a number in Python. Interesting enough, you can convert a string into a number in Python. Like if I were to do this, I think that, no, wait. Let me put something here. Maybe it should be a single quote. Wait, it's telling me here that you could do it though. Lies! Lies and fries! What was the difference between what I had there and what this is doing? Can you do A? Oh, it doesn't work with the, oh, because it's not base 10. What convert character into number Python? Oh, it's not a base 10 number, that's why. It's probably some like special, not a hex, but something else. Okay, it would actually be ORD. And it would represent as a Unicode character. Don't ask me how I got into this tangent. I'm let's just go with it. This is the stuff that helps you learn the nuances of a programming language. So I could do ORD to convert this into a Unicode like this. Look at that. Look at God. So therefore we have 97. Interesting. So now that means that you could actually pass in like number or formulas and stuff in here. So I could do like one, like I could do this. Interesting. You could add a plus 5. Okay, cool. Picasso. Let's ship it. Okay, so that's interesting. I think I got everything I needed out of that little module. Let's see. When it says A shape here, this is the dimensions. So this is like, the dimensions is 4 4 items in the array, and then I guess I could do, I wonder if I could do something like this. What if I could do that? No? How would I use NP array to make array an object exposing the array interface, object whose array method returns an array or any nested sequence? Could I do like this? No, you can't. I'm just trying to break it on purpose here. Sometimes you gotta do like that. So right now it's returning a 0-dimension object, which would be like this empty space here. I'm trying to see how I could get this to, I guess I would have to give it an explicit set of things. Like what if I did 2 arrays, or 2 like arrays here. That just doesn't work though. What if I put a bracket around it? Does that work? Okay, that does work. Okay. Let me copy this line here. I'm gonna put both examples here just for my own sanity. Now, could I do this? Wait 1 second, let me just copy this. Make sure that what I'm printing is the same. I forgot to update this one too, actually. So for this one, could I do like not recursive, but like what if I put in 1 array like that? Does that work? A ragged nested sequence is deprecated. If you want to do this, you must specify data type object when creating. Oh, okay. So it has to be uniformed. Otherwise, you have to specify data type as object. So let's try that. Let's try it. Oops, that's not what I meant to do. Data type. Object. Is that how it works? Yeah. Okay, so it just makes this into an object instead of an array of like a regular array. That's interesting. Okay, well that's good to know. I'm not gonna remember all of that, but it's fine. That's how it be sometimes. Okay, I'm gonna take a break here in a couple of minutes, a couple moments here. I'm gonna take a break and then we're gonna come back and play around with doing some operations. Ooh, holy muffler. Yeah, this is gonna be a 2-part series, I think, too, because I don't want to spend any more than like 2 hours on this today. And I'm seeing how I'm just like getting drawn. It's like all these like great tangents and everything. I'm new to Python. Well, Not entirely. I just really haven't sat down and looked at the nitty gritty of Python the way I am right now. So I'm actually okay with going on some of these tangents here, but they are going to make me take like a little bit longer to actually get through this lab, which it's okay. You know, I'm not going to complain about that. As long as I'm learning, like that's the key thing. So let me just see here. I think I might do one more of these little modules. Let's see. Oh, I lost my place. Okay, so just as a quick note here, so on dimensionality, and just as the example, what it says like for 2, actually I'm going to use variables here. We can say E, or we call it shape, it's S-H-A-P-E. And then we call this second one dimensions. And so that would be like 4, 2, which could be represented as something like something like this here. Just gonna go ahead and copy this. Right, so when we see 4, 2 as the shape, that shape, the first part of that's the shape, which is the number of different things, or how many times this dimensionality is like repeated, I guess. So dimensionality is like how many things exist within each of the items in this array. So for this, there's two things. And then the shape means how many items are in the overall array. And there's 4. So there's 4 items that consist of 2 items. Let me just, that's kind of hard to like, it's easy to understand, but it's hard to like say. That's with a lot of things. So let's say 4 indexes with 2 dimensions. An array with 4 indexes and 2 dimensions. Okay. Ooh, excuse me. I'm a little tired. Okay, so I think I'm just gonna add one more. I keep saying I'm gonna do one more thing and then I don't go. Okay, I'm gonna just call this vector creation. And then the next section we're gonna work on is gonna be called operations on vectors. Okay, so I'm gonna take a little break. As always, go grab yourself a little sneaky snack, some chips and dip, you know, some edamame if you're trying to be healthy, whatever you like, maybe a beverage. I'll be back in like 5 to 10 minutes. If you're watching this from the future, just go ahead and skip forward. Don't stress, don't be too pressed. I'll be back in 10 minutes or less. Hey, you're still here. I'm so excited. That makes me so happy. Thanks for coming back. Hopefully you got a snack. And we're gonna jump back into this now and work on operations of vectors. On vectors. Got a little typo there. Okay. So let's go ahead and get started here. We're gonna explore some operations with vectors using Numpy, of course, just to kind of see the different things that we can do in manipulating them. So the first thing we're gonna take a look at is indexing. Let's change my heading here to indexing. So elements, or let me make this bullet post. Elements of vectors can be accessed via indexing and slicing. With Numpy. Indexing, that's something we're going to define here real quick. We're going to define both of these actually before we get too far into this. Okay. Why doesn't it? I wish that I could have it automatically just keep my my little tabbing in my bullet points. Okay, so indexing means referencing the element, an array, by its position. And before I'm gonna go up here and fix some language. I call this say for elements with 2 dimensions. Okay, I want to have like some consistency in my language here. Okay, so referencing an element of an array by its position, and this is 0 indexed in terms of the programming. I think some other programming languages, I've never used one that's not 0 indexed, but I heard through the grapevine that I think R is indexed at 1. Is R language 0 index? I'm gonna look it up real quick. I don't know. I don't need to know this, but I'm curious. Yeah, the indices for the R programming language start at 1. Now, I've never used a programming language that does that, but that is very interesting to me. I don't know why that is the case with the R programming language, but I'm super curious why that decision was made, because every language I've used, Java, JavaScript, Python, Go, C#. I've never used C. I've used C++, which is like a superset of C. All of those are 0 index. So I don't know why R is different. It's interesting though. Okay, so slicing means getting. Oops, I went over too far. Slicing means getting a subset of elements from an array based on their indices. I spelled that wrong. Okay. So those are our basic definitions there. I'm gonna actually fix my formatting here just real quick. I'm big on my formatting. It has to be cute. My notes gotta be cute and pretty. I don't like messy notes, because I might need them in the future one day, you know what I'm saying? Or I might wanna share them. And I don't wanna be looking crazy. Okay, so now we're gonna do some examples of these. So, we're gonna create a vector first, and then we're gonna like do some stuff with it. So we're gonna be doing vector indexing operations on a 1-dimensional vector. 1D is not the band. Don't get crazy. Hopefully there's some one direction fans in here that can accept my little dad joke there. Okay, so arrange. We're gonna make a vector that, similarly to how we made this here of the range of 4, we're gonna make a vector that includes 10 indexes from values 0 through 9. That's what we're expecting. And this is how we do it. Bam. Okay, and I'm gonna go ahead and print that as well. Perfect. Okay, so now that we've done that, we're gonna access an element from this array. We're gonna access an element from that array, and we're just gonna do some print statements here. So formatted string here. So we're gonna be doing the third index dot shape. This should give us the size of wait, what does that shape do? Oops, got a little typo there. Dot shape. That's not what that's supposed to do. Stop messing with me. I need to figure out why I keep accidentally deleting my things here when I press Command Z. Okay, so I'm a little confused as to why it's having me do this part here. I'm gonna see, what is dot shape supposed to do? So a range dot shape. Should be array dot shape. Okay, so if this was I'm gonna just quickly replace the array that I have, which is a one-dimensional array, and put a two-dimensional. I think the reason why this is empty is because it's a zero-dimensional array, but if I were to put something else in here like this, it should be like, it should give me 2, 4. No, oh wait, I gotta assign it to the variable. Two, 4, and then this would be the second index of index 2 is outside of the what? Oops. What? Why is this? Why doesn't that work for this? Index 2 is out of the bounds for axis 0 with size 2. So I have to do that. Okay, so this is the size of each of the elements, or the shape of each element is 4. And the shape of the entire array is 2, 4. So it's kind of a meaningless thing to do. This. Oh wait, that does the 0th index, and if I do 1, it should be the same. Yeah, but if I do 2, it should throw error because there's no 3rd element in there. Okay, that makes more sense to me. Let me restore that back to what I had a second ago. So, what did I have? I think I had a range np a range 10. Why did I have turtle up here? My bad. Okay, so this here would be 2 dot shape. A2. So this is going to be the 3rd index within this array, which should be the number 2. So here. Like that. Perfect. And then what this is doing is it's accessing an element turns a scalar. So if this was an array that had, so if like this was an array where every element was 3-dimensional or 2-dimensional or whatever, this right here, this dot shape, it would give a number, but since it's 1-dimensional, it's just going to be 0. So okay, so that makes sense. I thought you had to do it like this though. Oh, that only works with a tuple. Okay. Huh. Would that work if I did it like this? No. Oh, I hate how I keep deleting it like that. I need to figure out what my shortcuts are that are making it where when I push Command Z, it's deleting. Let me save this real quick and go to Jupyter. Whoops. Look at my settings here. Oh, excuse me. That's not what I want. Let's go to settings. Preferences. I just want to see if I can see what my shortcuts are for Jupyter, because when I push Command Z, sometimes it deletes the entire block, which I don't like. And I just recently started using this to do Jupyter Notebook, so I still haven't really got my configurations. I know DD is to delete. Maybe that's what I'm accidentally doing, is I'm just accidentally pressing DD. I don't know. That is really annoying though. It's very annoying when I do that. Okay, anyways, I'm not gonna trip about it. I'm gonna do it again. I'm gonna be super annoyed to watch. This is how my brain works. It's super sensitive to distraction. Okay, so next one we're gonna do here is we're going to, oh, okay, so I think I had talked about this in a previous video, how if you do -1 as the index, it'll give you the last item in that array. So access the last element, negative indexes count from the end. So if I do print, format print, this is going to be a -1. It's going to equal. So this will give us the number 9 is what I'm expecting. Yeah. And I could do -2 to get the number 8. Okay, that's cool. Cool beans. And then I'm just gonna set something up here for this next one. We're making a catch for the exception here, which is going to be held in this object E, so that we can, it's just something you do for debugging. Usually a lot of like programming languages require you to have a catch when you do like a try or something like that. That way it knows what to do with the debugging. Also because you can use it to keep your code from completely failing, like altogether as well. It could be like a safety mechanism, but mostly for like debugging and logging bugs. So indexes must be within the range of the vector, or they will produce an error. So try C equals A. Oh, okay. Excuse me. So if this was 9, if this is index number 9, which would be the 10th value of which would be this number 9 right here, then this should print, right? But since, even though this range is 10, just remember that this is 0 index, so the 10th element is actually the 9th index. The 10th index is outside of what is included in this. So I'm just gonna put a comment here just for clarity's sake. So the range size, or length rather, is 10, but since this is 0 index, is the 11th element, which is outside of the range. Okay, so yeah, that's what we're expecting to see. That makes sense. So I think we can move on to the next thing here. do some slicing. Slicing creates an array of indices using a set of 3 values, which are start, stop, and step. A subset of values is also valid. Yeah, this is gonna be a 2-part video. I'm already yawning over here. Okay, so slicing. Okay, so we're gonna try a vector slicing operation. We're gonna set up our, we're just gonna copy this up here and use the same thing, basically. Okay, so that's our little array there. Access 5 consecutive elements. Start, stop, step. That's what each of the arguments, or I don't know if they're called arguments or if they're just called parameters when you're passing it into square brackets, but you know what I mean. You know what you'll see it. I don't know what it's called when it's square brackets. If it's just one, I know it's just like called index, but the definition of the slice maybe. Okay, so, and then we're gonna print something here. Tabs there all lined up. Access 5 consecutive elements. So we're going to start at the second index, which is here at this 2. We're going to stop at the 7th index. So 0, 1, 2, 3, 4, 5, 6, 7. I'm gonna have to look up some extra stuff here because I don't think this explanation I'm seeing makes enough sense for me. So numpy slicing. Okay, so this step means that we're going 1 over, but like if this was 2, I would expect that this would skip every other one. So it'd be like 2, 4, it'd be counting even numbers from 2 basically. 2, 4, 6. Okay, that makes sense. I just did it again. I hate when I do that. Okay, so I'm gonna change this to 1. And then what does the stop mean? Oh, I see. Okay, so the stop, when you do stop here, it excludes the end index, and start includes the first index in the slice. Okay, so that makes more sense now. So to kind of break this down manually, our start is at the second index, so 0, 1, 2, which is why we have 2 here. And then from here, we're gonna do this slice all the way up to the 7th index, but not including it. So 2, 3, 4, 5, 6, 7, but we're not gonna include it, so really it's gonna end at 6. Okay, that makes sense. Cool. So from there, yeah, we just have another example here, I guess. So I already did this a second ago, but I'm just gonna have it here for the notes. 2, so this is gonna give us 2, 4, 6. When I was when I was a junior developer, I don't think I'm like a senior necessarily yet, but when I was like a junior developer, I hated stuff like this. Like this kind of stuff and regex, like stuff like this. I was not having it. I was not having it. Not that I couldn't do it, but I just found it very boring. But now I feel like I have like more of a love for programming languages themselves. But when I first started out, I was like, no, I just want to make things. I just want to make the things and make them look cool and make them do cool things. But now I'm just like, okay, sometimes I don't really feel like I need to make anything with programming. I just like programming itself. I love programming in itself the way I love like math notation. I just love the language. But I used to hate stuff like this, stuff where I was like having to get into the nitty gritty. It was just painful. It was painful for me to think about. It was like, especially like having to do it under the pressure of needing to perform something. So like having to simultaneously learn something like that feels very arcane while also needing to, to have a deliverable at the end of the day. That just felt very stressful for me for a long time. So I started to learn to love programming in itself. Okay, so this next one here, this was accessing 3 elements separated by 2. This next one we're going to do is accessing all elements index 3 and above. So we're starting at 3, and then we're going to leave the we're going to leave the stop and the step empty. So let's go ahead and print that as well. I really could just copy and paste these print statements, to be honest. I'm just gonna copy and paste I kind of hate copying and pasting, but it's fine. I'll just do it this time since this is so tedious. Okay, so for this next one, we're gonna be accessing all elements below index 3. So that means that we're gonna leave. Okay, so we're gonna have nothing in the start. We're gonna do the step, and then we're gonna have nothing indicated in the. Okay, we're gonna leave the start empty. We provide a stop, which is also called an end of 3, the third index, and then we're not gonna do anything for the step. We're just gonna leave it blank. I'm gonna switch up this here, and that should give us, yeah, that looks right. Now I wonder if I do like just a colon at the end here, that also works too. Okay, I don't want to have the trailing colon there. I feel like it looks weird, so I'm gonna leave it here in my notes. But I think the trailing colon looks like it. Okay, looks like it does matter when you only have the start, but when you have the start and the stop, it doesn't matter. It's interesting. Okay, so I think we got one more in this little block here. Last one is to access all elements, which I think this would just be the same as calling the array. I don't know what the difference is, but I guess it's just like an alternate way at this point. Just that. Cool. I'm gonna just fix some spacing here, and then we're gonna move on to the next cell. Keep cute. Checking, make sure everything is correct. 0 through 9, 2 through 6, 2, 4, 6, 3 through 9, 0 to 1, and then 0 through 9 again. Calling the array. I'm gonna just check something really quick here. If I do this and I leave this empty, does that work? No, it's invalid syntax. Okay, if I do this, it's the same thing. So I'm just gonna leave that here just for my own clarity's sake. Okay. So now that we've done that, next thing we're gonna do is a single vector operations. This is basically taking the vector that we've created like this here, and then there's some methods that we can call on it that will do various things outside of slicing and indexing. So I'm gonna make a new markdown thing here, just to single vector operations. And then this needs to be Python. I'm gonna be here for probably another 20 or 30 minutes, and then we're gonna hop off. By that time, I should be about halfway through the little thing here. I'm gonna try to come back later on tonight. We're gonna see though. At least I'll have this done by tomorrow, because I just can't be doing this too long. I really got to keep pace, and whew, I just know for me, there's never satisfaction if I like rush through things. But then, you know, you can't take forever, because a lot of programming is like trying to be pragmatic in the face of the desire to do everything perfectly. Pragmatism says that you can't do it perfectly, so you need to know enough to be effective, and then you have to also be able to stay balanced. So as I'm trying to remember. Okay, so we're gonna make a new array here, numpy.array, and we're gonna explicitly define this one with just some numbers here. Okay, so we're gonna print this. And okay, so now we're going to take all of the elements and we're going to make them negative without having to iterate over all of them. We're going to make them negative. Now, because this is vectorization, what this is doing is going to be more efficient than iterating over the entire array and making them negative that way, because it's making them all negative in parallel, which probably doesn't seem like it's a big difference, but if you're working with larger data sets, it's a big difference, because parallel means that it's not going to do one number at a time. It's not going to do that conversion of each number at a time. It's going to do them all together in a multi-threaded type of way. Maybe multi-thread is not the right word, but it's going to do all in parallel. So negate elements of A. We're going to store this in a variable called B, so we can reuse A later on. So negative A is how we do that. Print E equals negative A, tab for life. And then this would be B. Cool. Got too many. Okay, so now all these are negative. Awesome. And then next thing we're gonna do is we're gonna sum all the elements of A and return a single scalar value. So sum all elements of A and return a scalar. To do that, we do .sum, np.sum, and pass in our array into it. So B equals np.sum A. I'm just gonna copy and paste this. I don't have to type it again. Cool, so it's 10. So 4 plus 3 is 7, 7 plus 2 is 9, 9 plus 1 is 10. I don't know why I did that backwards. Okay, anyways. Okay, it looks like we can also get the mean as well. I forget what mean means, so I'm gonna look that up real quick. I always get that mixed up. Mean is like the, it's not the average, average is its own thing. Mean and NumPy. returns the average of the array elements. So, okay, that makes sense. Mean is going to return the average of the elements. So in math, that means the sum of elements divided by array dot shape. Was it array size? Let me just say array size. I'm not gonna try to pseudocode that. So in this case, it'd be 10 divided by 4. So 10 divided by 2 is 5. 5 divided by 2 is 2.5. So that's what we're expecting to get from this is 2.5. So it's b equals np dot mean, pass in a, and then we're gonna print that down here. Just gonna copy this, take this, boom, bop, shabop bop. Okay, perfect, beautiful to me. Picasso, let's ship it. Okay. Okay, we got one more here. This is going to be squaring. Squaring all the elements, it looks like. So I'm just gonna go ahead and do this before I tell what I expect. So B, actually I'm just gonna do squaring all the elements. So it seems like whenever you call like the variable of your array, and then you do something on it like multiply or divide, it's going to do whatever that is for all of them. I'm gonna not just do a square, I'm also gonna add another one here for division and multiplication too, just to see if that theory holds up in a second. So I'm gonna do b equals a. In Python, star is square, star 2 is square, or like whatever number you have, you could do cubed or whatever. So take this line, copy it here. Boom, bam, bop, shabop bop. Okay. I don't know where I got that from. I think I got it from like some meme. Okay, so 1 squared is 1, 2 squared is 4, 3 squared is 9, and 4 squared is 16. Perfect. Now I'm gonna just copy this whole thing here, and I'm gonna just say multiply all elements of A by 2. Let's just call it that. So I'm expecting to get 2, 4, 6, and 8. Perfect. And then I'm going to try this with division as well. Divide all the elements of A by 2. So I'm expecting this to be 0.5, 1, 1.5, and 2. 0.5, 1, 1.5, 2. Okay, cool. Cool. Let me see. So how do I like describe this? Let me group these actually. I'm just gonna take these and group these. How do I make this make sense? When elements, or when the array is actually, I'm not gonna bother. I don't think it's gonna help me. It'll make me just waste time. What I was thinking is that there's some pattern here where I've proven that when you take the array, just whatever it is as a variable, and you do some operation like adding, subtracting, division, whatever, it's going to do that same thing procedurally over the entire array. And that seems to hold up across the base operations. Let me see if it works in modulo. Yeah, it works with modulo as well, so that's pretty cool. And then down here, you know, these are a little less weird because it's just assuming that these functions, whatever these do, we're going to do it across the array. But the thing I just found interesting is that in order to do these operations, you don't have to do anything special. That's pretty cool. I would love to know how that works under the hood. And does that actually work with just regular arrays? Oh, nope, it doesn't. So that is something that is specific to the NumPy. I'm gonna put that in my comments here. My sloppy fingers. Okay, so I'm just gonna add a little comment up here and say that, how could I describe that? Operations over the entire array, such as multiplication, division, addition, subtraction, and modulo work without, over the entire NumPy array, work without additional methods, but this is not true. This doesn't work with vanilla Python arrays, or with regular, why am I calling it vanilla? regular Python arrays. So this does not work with regular Python arrays. You will get an exception. Okay. Ooh. Okay, I'm gonna do one more little section here, 2 more code blocks, and then I'm gonna call this stream donezo. But I'm gonna take a little break here. I always say 5 minutes, and y'all know I'd be out for like 6 hours, so I'm gonna try to make it just 5 minutes though, because I really need to move on with my day. So just hold on tight. I'll be back. I'm just gonna stand up, stretch a little bit, warm up my chai, which is somehow colder than room temperature. I don't know how that happened. And then I'll be back to finish this up. So yeah, just go grab yourself some more coffee or whatever you want to drink, you know, and meet me up here in a little bit, okay? Okay, I'm back. I told y'all I be taking more than 5 minutes. I say 5 minutes, but just remember, when I say 5 minutes, that's like a very vague statement. Okay, I'm not trying to lie to y'all. I'm just not good at, you know, time things. I'm just gonna chalk it up to ADD. You know, they say people who are ADD are not the best at keeping track of time in the mind. So I'm just gonna own that. Anyways, let's go ahead and finish this up, or at least this part. I'm gonna have to come back for another part as usual. I'd be way too intense with my study sessions, but it's good because I learn a lot. But you know, it does take me a while to get through things because the whole point is not to just blast through this. So the last thing we're gonna do before I hop off of here is we're gonna do vector element wise operations, which I don't know what that means exactly, but we're gonna figure it out as we do these little code blocks. So and we're gonna make this like that. I think it's heading of 2, yeah, or no, it's heading 3. Okay, so heading 3, and let's see, what does it say here? Most of the Numpy arithmetic, logical, and comparison operations apply to the vector as well. These operators work on an element by element basis. Oh, okay. So basically what this means is that we can take 2 different vectors, 2 different arrays, which is vectors, and we can do things with them together, like add them together. So if you ever done like matrix or like array multiplication, that's kind of what this is doing. So we're gonna basically create 2 here. We're gonna make we're just gonna copy this one. So we got 1 here for A. Oops, this needs to be in a code block. Well, before I do that, let me put an example in math notation, because you know I love me a little latex. You know what I'm saying? I love doing math notation. Okay, so basically it's saying that if we make a new vector and vector named C, should be vec. A new vector named C, that is going to be equal to A plus vector A. Let me stop trying to talk at the same time. Okay, so remember that when it's like subscript I, this is referring to the element of the vector. So this element of vector C equals element of vector A plus element of vector B. So these are going to be like the same index. So 0th index, 1st index, 2nd index, 3rd index. I'm going to make a block here, and I'm going to define two vectors, 2 arrays. It feels weird to call a vector and array the same thing because I studied physics last summer. I'm not a physicist, but I studied physics last summer, and when I think of a vector, I'm thinking of 2 values. But in this context, vector is just an array, I guess. I need to go like look up what an actual vector is, because I have like these very like case specific, like these like domain specific ideas of it. But I need to see like what is the math definition of a vector, because this is like really annoying me to see like it used in these different ways. But that's neither here nor there. So I'm going to change this and just change up some of these values here, make this -1 and -2. And then okay, so binary operators work element wise. So we print and we're gonna add a actually what I'm gonna do is I'm gonna make C here equals A plus B, and then we're just gonna print off C. So -1 plus 1, or 1 plus -1 is 0, 2 plus -2 is 0, 3 plus 3 is 6, 4 plus 4 is 8. So that's how we got this here. Okay, I need to add one more thing up here. So, for with Numpy, most arithmetic, logical, and comparison operations apply to vectors on an element by element basis. And then this little notation here is kind of explaining what that means. Let me get rid of the bullet point, make this large. I like a good large latex here, so it's very clear to see. There's a space in there. So cool. Yeah. Okay, so of course the square must be the same size. So this is saying that the vectors must be the same size. If they were different sizes, we would get an error. We would get an exception. And I'm going to actually force that to happen here. So vectors of different sizes will throw an exception. So so C equals np.array, and then we're just going to make an array of size 2 with 1 and 2 as the elements. And then we're going to do a try. This is called a try catch, but in here it's not. Actually, no, this is a try except. But you might see like a try catch. Try except is like a try catch, except the whole point is to catch an error specifically. So that's what we're going to do here, similar to what we did up top here. Like here, we're going to do the same thing basically to catch this error. So we're going to make a new variable named D is going to be equal to A plus C. So A has a size of 4 and C has a size of 2. And then our exception catcher type exception as E. E is what we're going to use to hold, is a variable we use to hold the exception. We're going to print so error message you'll see is operands could not be broadcast together. I think that this thing here, when we say like an element by element basis, I think that's called broadcasting in Numpy speak. Let me just look that up real quick. Yeah, it's called broadcasting. Let me just put that in my notes up here before we end this little streaming session. Oops, I got lost. So we're gonna call this broadcasting this bold, broad, kappa, in Numpy. Denotes the ability to treat arrays as arrays of his ability to perform arithmetic operations on arrays on a element by element basis, or no, yeah, on an element by element basis. Actually, I think I need a better definition of this because I don't want this to be too confusing. I need to try to find a clearer definition. On array elements in a consistent way, and I think that's what I want to say. I'm just gonna make this, maybe add like a little thing there. Okay, and I'm gonna put this inside of a little thing like that. Cool. So I think this is what we have for now. I think this is good. This has been a long stream. This is 2.5 hours worth of just awkward computer techie goodness. I didn't dance in this video, and I also didn't turn on my colored strobe lights. So I think that means that we had a good old professional, like, put together, classy hootenanny. Nothing crazy over here, nothing strange over here, you know what I'm saying? Nothing to call home about. Just, you know, keeping it cute, keeping it casual, keeping it Gucci. I better save this before something crazy happens. Yeah, as always, this is just a study session. Don't be fooled. I'm learning this just as, you know, just as much as you're learning this probably. I will definitely though come back and review this entire vectorization topic at some point after I finish doing this lab and running through all of this stuff, because that's going to help me, also going to help you get a little bit clearer, concise definition in a shorter video format. These notes, like I mentioned at the beginning of this stream, these notes here are available though. These notes are available on my LinkedIn. They're like, it's like the first link down in the resources section of this video description. So go check that out. Vectorization is a really important topic. The reason why this is important, in case you missed it at the beginning of this video, is because when we're getting further into machine learning, we're going to be doing lots of things involving multiple features and different dimensionalities and sizes of vectors and stuff. And the way that Python is just built out of the box, it doesn't do parallel operations. So it'll be very slow the larger our data set gets, because it'll have to do arithmetic over every index, like individually. And what we get from doing it this way with this Numpy library, which does vectorization for us, is we get the ability to use the GPU essentially to do arithmetic and math and all this kind of stuff simultaneously with all the indexes. So that's going to dramatically decrease the processing time and the resources that are necessary to do things in an efficient manner. This doesn't matter so much when we're doing small things like just a simple linear regression with a small data set, but as we work with like larger data sets and do more complicated models and stuff, there would be a big impact on the amount of resources and time and everything like that. So that's kind of what we're moving towards. After we do this vectorization section, which will be finished up either today or tomorrow, then we're gonna kind of make this make more sense by doing multiple linear regression. So this is kind of leading somewhere. So please don't skip out on understanding at least the basics of vectorization, because it's something that's going to be more important as we work with larger and more complicated data sets. So with that, I will bid you adieu. Thanks for checking this out. I'll catch you on the flip side. Come back for part 2, okay? Bye.